Hey, wonderful students. Time for some AP Physics. I'm going to clarify something which I corrected myself in my period 3 A-Day, but I want to explain more in depth just to make sure you get it. We're going to talk about tensions and hanging things, and finally ramps. Hope your notebook's out. You're going to be writing a lot. You're also going to be asking me questions in class tomorrow or whenever you see me next to make sure you understood what's going on. Clarification. Here's the situation. You have M1 and M2 connected. The question is, what is the max acceleration M2 could have if M1 becomes super big? We're about to say that the max acceleration it's going to have is gravity. Here's the three words. If M1 is super huge, its force down will be its weight. However, it's connected by a string to this, which means these two are going to experience the same tension and they'll experience the same acceleration. So if this one's acceleration is at most gravity, even though it'll technically be a tiny bit less because there'll be a opposing force up here, if this is around gravity for its max acceleration, so should this. Furthermore, if this is such a huge weight, almost all that force is moving its inertia, and the remaining amount of force will be able to move this, but not faster than gravity. And I have a math proof here where I say this weight is the imbalance. So therefore, M1 times 10 equals MA. But what's the M here? What's the mass that's imbalanced? Overall, it's these two combined. And if you put a gigantic number in for M1, let's say you put in 1,000 and you put 1 in for M2, you will find that this is a little bit less than gravity. Okay, new situation. Here we go. We got 3 ropes. T3 is pulling up on this mass, and there's these two at different angles. We know this is at equilibrium. Therefore, we're going to say which one of these two tensions has got more tension on the string. We're going to say it's the more vertical one, because the more vertical it is, the more of the weight it's going to be resisting. We're also going to say that the x parts balance each other of these two. Since it's at equilibrium, therefore the left forces will equal the right forces. Now I'm going to ignore this tension 3 right here, because it is connected to these two and these two alone. So it's like I can just ignore it and say the 100 kilograms connected to these two tensions right here. So overall, it's like tension 2 is pulling kind of up left, tension 1 is pulling up right, and weight's pulling down. As I taught you, always draw a second with the components in. I define up as positive and right as positive. There is an equilibrium for y, and it's equilibrium in x. I'm going to show you right now that based on these angles and how they are right now, the y's are going to be the sine terms, and the x's are going to be the cosine. So I have 2 y forces up. I made them positive. 1 y force down, made it negative. And I plugged in what I know. Based on the picture here, opposite is sine. Notice I have gravity as positive 10 because the negative has already been taken into account with this negative in front of the weight. They're balanced, so the amount of imbalance is 0. If you were to solve for this, for T1 equals T2, you would find that T2 is a lot bigger than T1, where T2 is the 60-degree one. That automatically proves that T2 has got more tension than T1. But you already knew that because it's more vertical. And here we're going to show the x forces are balanced. And if you needed to, you could actually solve T1 in terms of T2. But I don't want you to do that. Look at this situation. T2 straight up, T1's at an angle. What can you conclude about it? Take a moment. And you're back. Here's what I can conclude. It ain't in equilibrium. It's not in equilibrium because there's an unbalanced x force to the left with nothing pulling it right. It will then accelerate to the left. Can this be at rest? The answer is technically yes for the first moment if you just let go or stop another force. So if it was currently in equilibrium right beforehand, because there's an x force to the right in order to balance out the left pull, then for that one moment you release the right force, it will be at rest even though there's an imbalance there. Kind of like in projectiles where if something's moving horizontally, the moment it enters the air, it will still have a horizontal only velocity even though gravity's pulling it down. It takes an infinitely small amount of time for gravity to start pulling something down. Which way is this moving? And the answer is no clue. We only know the acceleration. It could be moving right but accelerating left, or it could be moving left and accelerating left. All I know is accelerating left. That does not tell me anything about its direction, because the force from before could have been pushing it right, or there could have been no force at all. So now you're going to call this section ramps. You're going to need some room here. Draw this picture like 1 inch tall. There's an angle, there's a block, here's a ramp. It's pretty, so are you. Here's what I want you to look at first before you draw anything. Here's an example of the ramp with 30 degrees. Here is the weight pulling it down with 2 parts drawn in. And I drew this part myself just to show you about triangles. If you were to draw something right now, you would then draw just this weight and these 2 vectors. You don't have to yet. I'm going to prove that this angle and this angle are the same. Okay. Imagine this line as the edge of a triangle. So this is the opposite. This angle is 30. This angle is 90, which means this angle here is going to be 60. But this 60 degrees and this theta have to equal 90 because this arrow is perpendicular to the ramp. So this is 30 and this is 60. This also must be 30. These 2 angles are congruent. So now what I want you to do, because the acceleration of the block is either going to be up or down the ramp, the normal up, down, left, right, X and Y is not going to work anymore. Instead, we're going to rotate our heads kind of like 30 degrees. And we're going to say that it's a lot easier to say that up and down the ramp is the new X. And perpendicular to the ramp is the new Y. Once again, we're going to redefine our axes. We're going to say now that in this situation, up and downhill is to be like the new X. Perpendicular is to be the new Y. You ready to work? Weight pull straight down. That is neither in the new X nor the new Y. Therefore, I'm going to draw in the X and Y parts of the weight. So the weight is down like this, starting at the origin. I'm going to go down Y and over X. Based on the triangle I have here, where this is 30 degrees, the Y weight is weight cosine theta, whereas the X part of the weight is weight sine theta. Which one of these 2 weights is going to make this actually move down the ramp? Good. Your answer is going to be the weight X, since this weight is in the direction of the ramp. All weight Y is doing is pushing it into the ramp. It will not speed it up or slow it down the ramp at all, because WX, weight in the X direction, is in the direction of the ramp. So long story short, what we just did here is because the weight is no longer in parallel or perpendicular to the ramp, we had to find the parallel and perpendicular parts of it. So we also know there's a normal force here because it's touching a surface. The normal force is perpendicular, which is straight in the new Y. And we're going to say just now, not always, but right now there's no other forces. The normal force is equal to the Y weight. Under what circumstances would the normal force not equal the Y weight? When there's another force in positive Y or negative Y that will change it. And that's something we've talked about in the past. Now, from the block's point of view, look what we did here. Downhill is now to the left, uphill to the right. From the block's point of view, there's a Y part of weight pulling it down, an X part of weight pulling it downhill, a normal force up. Again, if there's another force, let's say, down like this, which would be into the perpendicular part of the board, the normal force would go up. An imbalance occurs. Which way is the imbalance occurring? Downhill. So it'll accelerate down the hill. Yes. Is it moving down the hill? No, no, no. It could be moving up the hill, but slowing because of that downhill imbalance. Or it could be moving down the hill and speeding up. Acceleration imbalance doesn't tell you which way you're moving. So we're going a little bit crazy right now. Here's what we did. Instead of X and Y, we're going to have a new X and new Y because it makes life a lot easier. New X is downhill or uphill. New Y is perpendicular to the hill. Weight in the X is sine of the weight. Weight in the Y is the cosine of the weight. Here's an example. You push on the box as shown. There ain't no friction. So you're pushing at that kind of weird angle. It's not in the new X. It's not in the new Y. It's kind of in both. 3 questions I want you to answer. Will the weight in X change? Will the weight in Y change? Will the normal force change? I'll wait. That's a little physics humor for you. All right, let's go. Let's draw a free body diagram to make sure. Here's the mass. There's the X and Y parts of the weight. They will not change because they're based on the Earth's pull. not at anything else. Your push will not affect the weights. So these two are definitely no change. Now, it's like you're pushing this way both up the hill and into the block. So there's an X part of your push and a Y part of your push. And there's a normal force. Does the normal force change? Absolutely. It gets bigger. Since the block is not going to move off the ramp, the normal force must be balanced with these two combined. So normal force has now gotten bigger by the Y part of the push amount. Like I said right there. How would friction affect this? Think. And the answer is it depends on which way the block is moving. Do not make the assumption it's because you're shoving a box, it will move in the direction of your shove. If it was super heavy, you're like Sisyphus. Sometimes you're pushing it up, sometimes it's going to overcome you and roll back down. So, if the block was moving downhill, which means its X part is more than your push, then friction would be uphill because friction opposes motion. But if you push more than if you push more than the X part of the weight, friction will be against your motion. So it completely depends on which way you're moving. You can't tell just from this diagram. And with that, my wonderful students, I'll see you in class.